It's wonderful to be here. I have a kind of a complicated relationship with TASI because exactly 11 years ago, I applied for what seemed to be an incredibly exciting program and was somewhat to my surprise rejected. Anyway, it turned out there are very good reasons why I was rejected. My application was not as impressive, evidently, as I thought it was. But still, you know, in a fit of pique, I vowed that if ever I would be invited to come speak at TASI, you know, I would say, screw you, forget it. You rejected me long ago, but then, you know, you're in the field, you have friends, your friends invite you, and you say, oh, sure. And then you come and you see what a wonderful place it is, and you realize, sorry? That was TASI 96. Well, I don't care. I'm past blame. You know, the wounds have healed. I have a scar to show for it, but it's all okay. That's right. That's right. But anyway, so I'm here for the second time as a lecturer, and it's impossible to resist the charms of the place. So, I'm very happy to be here. You know, but in thinking about that little story, I also realized how much, at least in my own mind, physics has changed since 96, and in many ways, at least I've never been more excited about the problems facing our field than I am now. Partially because of developments that took place over the last 10 years. You know, 10 years ago, of course, 11 years ago, the string duality revolution was just really starting to take off, and so that was extremely exciting. But still, at least in the sort of popular way of thinking about it, quantum gravity was thought of as a question having to do with the non-denormalizability of gravity, ultraviolet properties of the theory, what allowed us to make sense of very high energy scattering, for example. And I, at least myself, could never get extremely excited by that question because of a couple of reasons. On the one hand, it seemed like it was an incredibly detailed question. In our own world, after all, we know at very large distances compared to the Planck length, there's some effective field theory, the standard model coupled to gravity. Maybe there will be extra things beyond. Maybe there's a gut near the gut scale. But anyway, by the time you get to the Planck scale, there's all kinds of extra junk beyond, probably beyond what we've seen in the standard model. But all of that stuff has got to be relevant when you start talking about the very high energy scattering question. And so it seemed like even if you were successful at being successful at getting an answer to that question would involve really all the details of the theory, everything to do with the particle content, the masses, the couplings, everything. Of course, for a long time, that was also the hope that progress on this question meant getting the whole thing, getting the whole answer, finding that, in fact, that long-distance theory was more or less unique. You could predict all the parameters, and as a bonus to being able to predict all the parameters, you'd also have a fully UV complete theory of gravity. So it seemed like at least the question as posed seemed a little limited. What's going on when you scatter things at very high energies? And the nature of real big progress seemed to require just getting the whole thing in one go. I'm telling you my own naive thoughts. Of course, much of this is wrong, but some zeroth order spirit of it is still right. Associated with that was also something which bothered me, I think bothered many people, that if quantum gravity was supposed to be about figuring out what happens when you scatter things at energies way above the Planck scale, you know, sort of analogous to the Fermi theory breaking down when you scatter things at energies far above the weak scale, well, the situation seemed to be a lot better than the Fermi theory, because in the Fermi theory, we really didn't know what happened ahead of time when we scattered particles at energies above the weak scale. But in gravity, we do know ahead of time what happened when we scatter particles at energies way above the Planck scale. We make black holes. So we've known that since antiquity in this subject. We make black holes, and the black holes Hawking evaporate. And of course, you would need to know the full underlying theory of gravity to figure out what happens in the transition between energies way above the Planck scale and way beneath the Planck scale. But that seemed to be some meager pickings for such a grandiose thing as a theory of everything to allow you to compute in detail what happens in the transition between a well-understood high energy and a well-understood low energy phase. So anyway, that seemed to be sort of what quantum gravity was about. And on the other hand, in thinking about physics at more accessible energies at the TeV scale, there too, the set of possibilities were pretty much constrained. This was fresh off the spectacular success of the supersymmetric prediction for the unification of couplings that was verified at accelerators both at SLAC and at LEP, which for the first time measured the coupling constants precisely enough to be able to see that when you extrapolate supersymmetrically the couplings to high energies, they converged very accurately to the sort of percent level at the gut scale near 10 to the 16 GeV. So, you know, this was very high times for thinking that something like low energy supersymmetry was correct. And so all of beyond the standard model building, or most of it done by sensible people, everyone had sort of more or less agreed we knew the basic big answer to the question. It was low energy supersymmetry. Then it was all about which variety is it? Is it this kind? Is it that kind? Is supersymmetry broken this way and transmitted by gravity mediation? Is it broken that way and transmitted by the gauge interactions? Okay, it was fun, and that's what I did. Those were the sorts of things that I thought about for my thesis. But still, the sort of scope of the questions that were left seemed pretty on the sort of very grand scale of things that got most of us interested in physics, things like quantum mechanics, relativity, and so on. It didn't seem to be of the same sort of caliber question. Well, I think it's fair to say that what's happened in the last 10 years, including tremendous theoretical progress internally in string theory, is that also experimental hints, both from cosmology and a growing collection of more indirect hints from experiment in particle physics, make the situation now much, much more confusing than it was 10 years ago, and make the questions that are open and the sorts of questions that we're asking, I think, a lot more fundamental seeming. For example, as I'm sure you heard in a number of the previous talks, the fact that the universe is accelerating and that there has to be a tiny cosmological, or the most plausible explanation is a tiny cosmological constant, closed a hope that many people had that the one major outstanding mystery that was left having to do with gravity at long distances, namely why is the vacuum energy small? Everyone hoped that there would be some dream miracle mechanism for making it zero exactly, and after we see the universe is accelerating, and that the vacuum energy is a tiny non-zero value as the most plausible explanation. Well, that explanation doesn't seem to hold water anymore. And coming to grips with that tiny vacuum energy, as I'm sure you all know by now, having sat through 3 weeks of this school, has triggered probably the biggest crisis in theoretical physics in the last 20 or 30 years. The best explanation we have so far, maybe someday we'll find a better one, but the best explanation that we have so far for why we can find the universe with a tiny vacuum energy does invoke the huge number of vacua that also developments in string theory seem to give us. But immediately, forget about the anthropic principle. Immediately, just the mere existence of 2 of those vacua, never mind 10 to the 500 of them, opens up a whole new set of conceptual questions about how to think about cosmology. Indeed, even our own accelerating universe opens up the same set of questions for how to think about cosmology. Our universe is accelerating. There are regions beyond our inflationary horizon that we'll never see again. And there are good arguments put forward that we can't make sense of a theory just of that pure de Sitter space all by itself. And so that means that there's got to be somewhere else that the theory can go. Minimally, there should be one other place for you to be able to get out of this de Sitter phase into. So at least one other vacuum. And well, the fact that we seem to get that we seem to get 10 to the 500 gives us a plausible reason why some of them should have a small enough vacuum energy in order to be compatible with what we see in the universe. Even ignoring the words of the anthropic principle yet for trying to come up with why we live in that, trying to rationalize the particular value that we observe. Simply the existence of all that many vacua makes it possible to find a universe compatible with the value of the vacuum energy that we see. But the conceptual puzzles that are opened up is how to talk about our world, which is inflating, which is accelerating, which we will tunnel out of. How do we talk about that cosmology? How do we talk about doing physics? What are we supposed to compute? If someone handed you a fundamental theory of everything, whatever that is, what would you want to compute in such a universe? Are there any precise observables to compute in such a universe? Because it's cosmological, because we only have access to a finite number of possible measurements that we can make inside a Hubble volume. This opens up all sorts of questions about quantum mechanics and cosmology that were always there anyway. They were always there anyway. They always had to be confronted anyway. But the presence of a landscape makes it crucial to confront these questions in order to have any notion of predictivity or even what we're supposed to predict, versus the sort of more canonical monovacuistic point of view, where you would hope that all these cosmology questions would sort of factorize. They're always deep problems, but they would always factorize, and we would at least figure out what vacuum we live in. It would be unique, and we could make all sorts of predictions for other things. But no, if there's many vacua, we cannot decouple these deep, important questions about quantum mechanics and cosmology from questions about vacuum selection then and predictivity. All of which is to say, and this is something that will be the theme of the next 3 lectures, that it seems to me, and I think to many people, that the really deep questions about quantum mechanics and gravity have very little to do, or only indirectly to do, with the short distance properties of the theory, and instead have to do with trying to understand how to make sense of cosmology. Causally disconnected, classically, causally, or semi-classically, causally disconnected regions very, very far away from us. And there are good reasons to expect that quantum gravitational effects might be important in such a situation, despite the fact that they naively don't seem to be. And anyway, this will be the theme of the next 3 lectures, as I said. But there's clearly something missing. There's clearly a big conceptual point missing, and even how to make sense of this picture. I'm sure Raphael talked about attempts to put measures on the space of all vacua. I'm sure you've all seen this, and we'll review it again starting tomorrow. You've all seen this famous picture of the fractal Penrose diagram corresponding to an eternally inflating universe going from one vacuum to another vacuum to another vacuum to another vacuum. And many of us have stared at this diagram intently for the past 2 or 3 years. And I don't think anyone has really made any heads or tails of it yet. And it's clear, at least it's clear to me, that there's some important conceptual point missing. And it doesn't have too much to do with the detailed properties of the standard model. It doesn't have too much to do with anything about the X or Y detail of this or that fermion mass or this or that pattern of supersymmetry breaking. It seems much more kinematical. It seems much more fundamental. And if I had to guess, I would guess that making progress on that question is going to take a step of sort of comparable size, maybe not quite as big, but maybe as big as the step that was required in going from classical mechanics to quantum mechanics. And so that's one reason I say I'm so excited, even purely theoretically, even though we're confused, especially because we're confused. It seems like the things we're confused about are finally about really, really, really big things. And that it's conceivable that what's needed is some real conceptual breakthrough Well, you guys should be even more excited about that than I am, because physics isn't always, progress in physics isn't always triggered by people with revolution on their mind. If it was, we would all know what to do. Every day revolution, right? But it's not like that. It's not like that. If it was, life would be easy. It's not like that. And at any given moment, either revolutionary or conservative ideas are needed, and you never know which is which ahead of time. So in the first part of the 20th century, first 30 years, revolution, revolution, revolution. Every problem, the answer was revolution. Okay? The next 70 years, it was exactly the other way around. Okay? The next 70 years, every problem, the answer was conservative. Okay? And in fact, these poor guys like Oppenheimer, Bethe, people like that, who sort of came in on the tail end of quantum mechanics. They're like, hey, I can do what these guys did, right? Every problem, okay, revolution, revolution. And the old guys were trying to solve all the problems by finding revolutions, and they're all wrong. And the generation of Feynman, Schwinger, Gell-Mann, the whole generation that went into the development of the Standard Model and up to today, was over and over again the triumph of the conservative idea over the radical one. In this case, it was the youngsters in the 40s and 50s playing the role of the conservatives, saying, no, you guys, you Heisenberg, you want to introduce a minimal length, and Pauli, you want to do some crazy thing, and Bohr, you even want to throw out energy conservation, you guys are all nuts. All we have to do is take quantum mechanics and E&M and just compute. Just have to calculate. Nothing fancy. You just have to sit down and calculate and do it properly, and that was the right answer. Okay? And really, every single time again, there was some hint or evidence that something really strange and wild might be afoot. It wasn't. Okay? The answer ended up being conservative over and over again. It might be that the pendulum is swung, and that these questions that we're struggling with now are going to need a revolutionary answer. I can't, again, if I knew for a fact, it would be a lot easier. But it certainly smells to me a little bit like that. At least the nature of the question has the same kind of feeling. In the early days of quantum mechanics, a lot of what people struggled and obsessed over was what they should be asking anyway. What questions they should be asking, what physics was supposed to be about, what you were supposed to compute. Before the Bohr atom, but after the Planck blackbody radiation formula, it was clear that there was something wrong with classical mechanics, but it wasn't clear what. And it was certainly not clear what you were supposed to be doing instead, exactly. All there were a few phenomenological hints. There was the Planck blackbody formula. There was the photoelectric effect. But no one knew exactly what should be quantized. And this gave the older physicists of the era enormous headaches. So people like Lorentz complained incessantly about, and they even used this exact language, of not giving up. It was very important not to give up a classical picture, a deterministic picture of what was happening. That was what physics was about, after all. And Einstein, even Einstein, who, as you know, helped usher in quantum mechanics, from very early days had exactly the same general unease about the whole thing. This I only found out recently, that he had actually been playing with an analog of the Bohr atom, but hadn't published anything. And was very impressed when Niels Bohr's paper came out on the Bohr atom. And on their first meeting, he told Bohr, well, I was doing the same thing, but I didn't pursue it, because if something like that is right, it means the end of physics. Okay? Exactly the same language. I mean, I find it very telling that it's very much the same kind of word, the same kind of angst, the same sort of issues at stake. What are we supposed to compute? If we're not supposed to compute the masses of the elementary particles, if the vacuum isn't unique, if there's 10 to the 500 vacua, well, what are we supposed to do? What is physics supposed to be about? I think there's definitely a clue there that associated with this large number of vacua is this very confusing picture about cosmology. And trying to make sense of that very confusing question about cosmology has got to be tied up in an important way with even figuring out what we're supposed to compute, what the output is supposed to be, is what the mathematically well-defined quantities we're supposed to be computing. All of which to say, just that purely on theoretical grounds, the extreme confusion that we're going through feels very, very fertile to me, despite the fact that we're not making a lot of progress. It seems to be, I think, possibly a time for some really radical, interesting idea, and therefore a time for 25-year-olds to take their rightful place in the pantheon of theoretical physics again. And hopefully, those of us who are a decade or so older might be able to pull a Schrodinger and make some little contribution as well. Okay. And also, so that's purely theoretically. At least I myself, you know, I started off life thinking only about models for physics beyond the standard model, not too much interested in string theory, not too much interested in quantum gravity. And all of these questions that have come up, especially in the last 5 years, especially triggered by the landscape, at least my own interest in these questions has never, ever been greater. On the other hand, of course, it's also incredibly exciting times because of experiment. The LHC is turning on next year. That's no longer a translationally invariant statement, as it has been for a long time. So actually, for a long time, it was 5 years. So now it's really not a translationally invariant statement. You know, it's glorious. It's spectacular. Our experimental friends are to be commended. And we're going to start learning something new about the TeV scale. And you know, everything in the first part of what I was telling you about, the cosmological constant, the landscape, everything here is high drama, as you all know. Okay, but a very similar story at a much lower level of volume has been played out in particle physics over the last 10 years. So you know, we had these issues about which is that there's just more and more hints, or in a sense, more and more absence of hints that there's new physics beyond the standard model. It's not conclusive at all. It's not conclusive. We might just be panicking about trivial little things on the grand scale of importance. But certainly, particle theorists are far less confident in what's going to happen at the LHC than they were 10 years ago. So 10 years ago, it was, yeah, for sure, there's going to be a natural explanation for electroweak symmetry breaking. Obviously, it's supersymmetry, duh, right? It's low energy supersymmetry. And then, okay, you're a gravity-mediated guy, and let's check out your soft masses, and ooh, look at your gauge-mediated soft masses and make all these predictions. And now, again, the very zeroth order issues are on the table again. It's not clear that there is going to be a natural solution at the hierarchy problem revealed at the LHC. There very well might be. And you know, I wake up every other day flipping back and forth about what I expect to find. But there are certainly reasons, and there's a trend of evidence that suggests that we might not be seeing that. Well, that's sort of dramatic in itself. And so what's at issue with the LHC is more zeroth order. Even seeing, first of all, what is it? Is it natural or not? That's back on the table. Of course, if it is natural, well, if it's supersymmetric, or if it's this or that version of extra dimensions or whatever, we'll sort it out. But that'll be very much along the lines of what we expected. But it's quite plausible that we'll reveal instead something that does not look natural at all. And if we see at the LHC something that looks very, very unnatural, then that dovetails very obviously and nicely with the biggest result in cosmology of our lifetimes, that the cosmological constant appears to be non-zero and also unnatural. And I think such an observation would push us even further. It wouldn't be conclusive. It wouldn't be direct proof. It would just be more circumstantial evidence that something like the landscape is real. So anyway, so those are the reasons why, didn't mean for that to take so long, but those are the reasons why, at least to me, physics is, I guess I can say I wish I was 25 now rather than in 1996. Anyway, not much I can do about that. So what I want to do is talk about a little more concretely what about the questions that the possible presence of a big landscape of vacua raises for particle physics and these deeper questions about cosmology. And I'm really going to divide this into two parts. Today I'm going to spend talking about some of the particle physics implications, and the rest I'll talk about some of the cosmological questions. And the cosmological questions are, no surprise, they're hard. Okay? The cosmological questions are hard. It's not obvious, again, what questions to ask. It's not obvious how to begin making progress. But I'm going to try to at least tell you a few things about it, at least some of my own struggles with these questions. But there is something that one can do without understanding all the details of the landscape and gravity and cosmology and all of those things. There's something that you can do sort of taking inspiration from Weinberg's explanation of the tininess of the cosmological constant. See, Weinberg didn't even know about all the complicated issues of the string landscape when he made his prediction for the vacuum energy. You just have to believe that there are lots and lots of vacua. In some sense, they're populated. In some sense, we're allowed to talk about all of them. And then to find some parameter in your theory that is normally, some parameter in your theory that seems to be finely tuned, and try to see if you can come up with an explanation why it's finely tuned, invoking the presence of lots and lots of vacua by saying, analogously to what he said for the cosmological constant, that if this other parameter had values that were outside some very, very narrow range, some disaster would happen in infrared physics, and the universe would look incredibly different than the one that we see. Okay. So this is something that you might call the principle of living dangerously, that you want to take some parameter. In Weinberg's case, it was the cosmological constant, and it has a whole range of possible values that it could have between -1 and 1 in Planck units, but only in a really minuscule range do you get, only in a really minuscule range between 10 to the minus 118 and minus and plus 10 to the minus 118 in Planck units, is that, do you get a universe that isn't empty, at least holding all the other parameters fixed? And then you get to make a prediction. Then you get to make a prediction that the value of this quantity should be pretty close to that edge. Okay? It should be pretty close to that edge. If it wasn't close to that edge, well, there's got to be some other explanation for why it's small. But if it's just this sort of random statistical environmental explanation, there's no reason for the parameter to be so much tinier than what's necessary in order not to sort of totally screw up the IR properties of the universe. So you can make this sort of argument even without knowing about the detailed properties of the landscape and how it's populated and so on. And so what I want to talk about is what this point of view offers to possible physics at the TeV scale beyond the standard model that we might see at the LHC. In other words, I'm going to argue that the presence of the landscape motivates you to think about theories that you would, very concrete theories, very specific theories, motivates you to think about concrete specific theories that you would never have otherwise thought about or proposed or even thought had any chance of showing up in nature. Theories that will look very finely tuned. They will not look natural. They'll look finely tuned. But so they look incredibly implausible from the usual monovacuistic picture of the world. But they're reasonably plausible if you believe that there is a landscape. And since this is model building, we have much, much lower standards. We don't have to solve everything. We don't have to understand everything. The goal of a model builder is to find some set of principles that they can apply to try to construct interesting theories that make very sharp predictions. Those theories will be tested one way or the other, up or down. Independent of the motivations that got you to those theories, the goal is to come up with whatever private motivations you have. In the end, is to come up with very, very testable theories. So the landscape just offers us another tool in the model building toolbox. It allows us to relax one of the rules that we always used to impose. The theory at the weak scale should be natural. Okay? It allows us to throw that out, but not to do completely random things. We're not allowed to construct totally random theories. They have to be unnatural theories of a very specific type. They have to be unnatural theories where the only parameters which are unnatural and are finely tuned are associated with some obvious disaster, okay, and are living dangerously. If they were a little different, the infrared physics would be horribly, horribly different. Okay? So it just gives us a new way of thinking about building models. And so thinking along these lines, you make specific proposals for models, and models may or may not be confirmed by experiment. Okay, so this is the more modest thing that I want to talk about today. Before doing that, I want to not go 25 minutes without writing down an equation, although that would be an all-time record for me. Let's just wait, shall we? I'll just keep talking. I want to talk a little bit about the idea of naturalness. I'm sure Martin talked about it as well. I'm not sure. Did Martin tell you anything about the sort of historical antecedents of this idea? Okay, so this is a little bit worth going into because he probably explained. He explained it, right? Why? Okay, good. So because I'm going to spend a lot of the rest of this lecture bashing it, and because there seems to be some hints from experiment that there's maybe something a little wrong with this idea, I really want to tell you this is a damn good idea, okay, in the sense that it's worked over and over and over again in the last century. And I want to give you 3 examples of situations in the last 100 years where there was some quantity and some theory that appeared to be finely tuned. If you believed in the doctrine of naturalness, you would believe that there should be some new physics that comes in at a specific scale in order to solve that fine-tuning problem. And physics came in at exactly that scale, in fact, earlier, in order to solve the fine-tuning problem. So this isn't a crazy idea, okay? It's worked over and over again. And so let's just go through the examples briefly. Probably many of you have seen examples like this. The first example goes back to 1900 and is the classical model of the electron. Okay, so if you take the classical electron, then, Abraham and Lorentz and people like that thought the electron was point-like. But they knew that there was an electric field around the electron. Maybe there's a 4 pi. And if we then look, let me not even bother with 4 pi's. That's an affectation. If we look at the energy stored in an electric field, as is famous, that energy is divergent, right? Because E squared, electric field squared, so this is the energy. So E squared goes like 1 over r to the 4th, so this goes like E squared over r to the 4th. So this is going like E squared, like the integral dr over r squared. So this is linearly divergent as you go to short distances. Okay? So if we say that there is some size here, a, and we cut this integral off at that size, what do we get? Well, we get the energy is E squared over a. And these guys figured that, there had better not be unnaturalness. In other words, A had better not be so tiny, that this contribution to the energy overwhelms the classical mc squared of the electron. Okay? So, that tells us what size the electron should have. Okay? And that size is called the classical radius of the electron. That happens when E squared over A is equal to m electron c squared. Okay, so this distance is E squared over m electron c squared. Okay. So of course, they weren't using the words naturalness and so on, but rephrasing this problem in a modern language, we would say that something has got to happen beneath a cutoff of around A, E squared over m electron c squared. Some new physics has got to come in order to soften this divergence so that we don't have to cancel enormous contributions to the energy off against each other to understand why the electron has the mass it does. Okay. Now, what did they do? They tried to build models of little rigid spheres. Okay. And you haven't heard about it because they all sucked. Okay. It's very hard to build models of rigid anything in relativity, in fact. It's not for lack of trying. There's a good reason. It's because the notion of rigidity is a very hard one to have in a relativistic theory. But anyway, there's a long story that we don't need to know because that's not the answer. Okay? Something else happens far before we reach this scale. Does anyone know what it is? What actually cuts this off? Anybody? Those are words for what cuts it off. But what? What is it? I mean, there's got to be something new coming in, right? There's got to be something new coming in. Huh? It's antiparticles. It's exactly antiparticles. Okay. And you know, if I want to say colloquially, it's because really there's clouds of electrons and positrons around the electron. This length scale is what? That length scale is h bar over mc. First of all, there's a new constant they didn't know about h bar, but there is a typical length scale around h bar over mc for the size of the virtual electron-positron cloud. And the problem is, when you have all these virtual electrons and positrons, again, colloquially, you don't know which the electron is. Is it that guy? Is it this electron? Is it that electron? You don't know which one it is. Okay, and that's what cuts off this classical contribution to the energy. Okay. And if you say it a little more, formally, in old-fashioned perturbation theory in quantum mechanics, this effect is I won't go, but the classical contribution to the energy looks like a diagram like this in old-fashioned perturbation theory, and there's the canceling diagram with the antiparticle. And together, the linear divergence cancels. But what I want to point out is that this length scale, so these classical guys, if they're using naturalness, would predict that something new should happen at distances bigger than A. Okay, I mean, no one says that this contribution has got to get right comparable to the mass of the electron. It could stop earlier. Okay. And this distance is bigger than A. H bar over mc is bigger than E squared over m electron c squared to the extent that, what? 1 is bigger than E squared over h bar c. Well, this is our famous friend alpha, which is the weak coupling parameter, 10 to the minus 2. Okay? So precisely to the extent that alpha is small, the positrons cut off this divergence even earlier than was needed from the point of view of the classical guys. Yes?
So, curiosity, when we first considering this problem,
oh, crap. I mean, because, what's his name? Thomson had just discovered the electron 2 years previously. So the answer is I don't know. I mean, but I'm assuming really, really bad. Okay. So here's an example where this philosophy kind of was used without them spelling it out, and it wasn't wrong. They were wrong about the particular model. Comparing to the hierarchy problem, you know, they guessed Technicolor, wrong. Okay, but still, there was some new physics that came in. It was more exotic. It was more interesting. In fact, probably many of you have seen this in colloquia. There's a literal analogy between this and supersymmetry. Because what actually happened, what actually solved this problem, is that we discovered an extension of space-time symmetry in quantum mechanics, relativity in quantum mechanics. Relativity in quantum mechanics predicts antiparticles. So relativity and quantum mechanics together, an extension of our notions of space-time symmetry plus quantum mechanics, doubled the world, doubled the number of species, and those partners came in to cancel this linear divergence. Okay. And if we discover supersymmetry as a solution to the hierarchy problem, then I guarantee that the high school textbook stories will be morally similar. Okay, we'll discover another extension of our notion of space-time, yet another doubling of the number of degrees of freedom of the world, and again, it came in to solve an ultraviolet problem. Okay. So let's do more recent examples. This one is just the spitting image of the hierarchy problem. Okay. Imagine a world where there's no up and down quark masses at all. Okay, but it's QCD with no up and down quark masses. So we still have chiral symmetry breaking, blah, 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 Goldstone bosons. Okay, so we have pions, charged pions, neutral pions. But the chiral symmetry on the quarks in the underlying QCD theory is broken by the electromagnetic interaction. Okay? And so in the low energy theory, there is a difference between charged and neutral pions. The charged ones are charged. Okay? So there's no reason why the charged guys and the neutral guys, there's no symmetry. You know, if we turn off E and M, there's an SU2 symmetry that rotates them into each other. Okay, but if we turn on E and M, there's a difference between the charged and the neutral guy. And so we should expect a mass splitting between them. Okay? Now, so here we are. We've seen pions at low energies. There's some cutoff scale lambda where we don't know what's going on. But beneath that cutoff scale, there's a charged pion and a neutral pion. Now, how would you estimate the mass of the charged pion? Well, in this low energy effective theory, this pion just looks like a garden variety charged scalar field. You don't know that it's supposed to be called a pion. Okay? So you draw a diagram. Same diagram that you draw for the Higgs. This diagram. With a photon running around the loop. Okay? And its other friend. Okay? There aren't any analogon, if that's a word, diagram for the neutral guys. Okay, so there's that diagram. Okay, well, so what does this give you? You say m pi squared, pi plus squared, from here should be around e squared over 16 pi squared times cutoff squared. Right? Okay. Sometimes you'll see in papers people talk about the hierarchy problem and mumble, maybe there are no quadratic divergences. You know, maybe if we use dim reg, there's no quadratic divergences, so there's no hierarchy problem, mumble, mumble. Okay, and they don't say it very loud because these arguments have been recycled for almost 40 years now. And if you don't know what's wrong with this argument about dim reg, by the way, I encourage you to do the little exercise yourself to see why dim reg doesn't make the hierarchy problem go away. I'd be happy to talk about anyone who's interested in talking about it afterwards, but you should really do it yourself because it's a lot of fun. Okay? But anyway, you don't need to worry about it, you don't need to pay attention to any of these papers because in the case of QCD, this is not only the right answer, this is not only right, it gives you basically the right answer numerically as well. That is the charged pion mass, so the pi plus pi zero mass splitting, a big contribution to it. If for the cutoff you put the scale where new physics comes in. The scale where new physics comes in as far as the pion is concerned is actually the rho meson. But you can think about it just a little more roughly as the GeV scale, the QCD scale. Okay. So it's right, and this is the right answer, and it's the right magnitude for the charged pion mass. Okay? But we can also invert the argument. We can invert the argument and say, we saw this quadratic divergence for the pion from the observed value of the pi plus. We would infer that there should be some scale beneath which new physics comes in. And it does. The rho meson comes in at that scale. In fact, it comes in again beneath that scale. It's in fact very much like our previous example where the new stuff came in at a length scale that was parametrically lower. A length scale was parametrically larger than was needed, parametrically by a weak coupling factor. In that case, it was alpha. In this case, the rho meson comes in, again, numerically a little bit beneath the GeV scale. It's in a 770 MeV. In the end, there is a kind of parametric explanation for it because QCD is a little weakly coupled as a large N theory with N equals 3. It has a little bit of a small coupling, 1 over N, 1/3. Okay, and that 1/3 is ultimately responsible for why the rho meson comes in even a little earlier than it needs to. But in both of these examples, the new physics indeed came in right where it needed to, even before where it needed to, and it solved the problem. The final example, so anyway, I hope you see that this is morally identical to the hierarchy problem. Okay? I mean, it's the same diagrams. All right. The final example is was one of the arguments that led Glashow, Iliopoulos, and Maiani to predict the mass of the charm quark. So if we take the weak interactions, and we make a loop diagram with only up quarks in the loop, and we compute the mass difference between k and k bar. Okay? Well, this is very easy to do just in the low energy theory. You don't need to know anything about W's or anything else like that. You just take the 4 Fermi interaction that you know you have. Then you get a mass splitting between k and k bar, which turns out to be, again, quadratically divergent. So this ends up being proportional to some powers of G Fermi, but there is a quadratic divergence. Okay. And now what Jim argued was that something new has got to come in beneath that scale in order to make the left-hand side comparable to the observed value for the KK bar mass difference. Now they had a specific, just like we do in beyond the standard model of physics today, you can't just throw in random new particles. It has to be something that cancels the effect, right? So they had a specific model in mind, charm. Okay, the charm quark cancels this loop diagram, but it's got to cancel it early enough, unless you want to, again, imagine there's some kind of fine-tuning conspiracy, something like that. So this led to the prediction that the mass of the charm quark should be less than around 2 GeV. Okay. And indeed, it was found at less than 2 GeV. It was found at 1.3 GeV. Okay. In fact, in our current understanding of the standard model, this sort of naturalness argument is even a little more vindicated, because actually in the standard model there's 3 generations, and there's also a contribution to the KK bar mass difference from the top loop. Okay? And those 2 contributions are comparable. No actually very deep reason why they have to be comparable, but they're kind of close to each other. One could have imagined a theory where the charm quark was a lot heavier, and you played around a little bit with the rest of the spectrum and the CKM matrix to cancel off the contributions to keep delta MK at the value that it did, but that's not the way it worked. Okay, well, they had the sort of simplest possibility, And nothing ended up looking very tuned, and everything was perfectly natural. Okay? So, people are not nuts for thinking about naturalness. Okay, this is a perfectly plausible idea for what might happen. The problem is that in all of these examples, naturalness worked in a really big way, right? You know, we just saw it. There was no if-butology. There was no, well, it didn't quite work. Maybe 10% fine-tuned is okay. 3% is okay. 2 things cancel to a part in 30. None of that, right? You know, something had to happen, and it happened like whomp. Okay, no problems. The problem is that when we think about the hierarchy problem, because of all kinds of indirect limits, it looks like at least almost all the nice theories that we talk about for solving the very big hierarchy problem all suffer from a little hierarchy problem. And I'm sure Martin talked about this, right? So did Martin talk about how every theory kind of sucks? Every theory is tuned to the sort of percent level? Okay. So now I should say that this could reflect a failure of nerve and imagination on the part of model builders. Okay? Maybe we've been playing for 20 years. We're really tired. You know, the LHC is turning on. We don't want to do any more work. And we're just really lazy. And if someone worked harder, they would find that brilliant, beautiful mechanism that solved all the problems. It wouldn't be tuned at all. And PH is filled with papers by people that are not me on beautiful solutions to the little hierarchy problem. Nothing's tuned. Everything is great. Life is wonderful. That may well be right. I really want to stress that. I mean, that's not the attitude I've been taking for the past couple of years for a variety of reasons, but it really very well may be right. At least my own personal problem with this is that I've tried this sort of exercise myself, and what I've concluded, at least from my own humble attempts, is that we can take this 1% tuning and we can break it up and push it around in 3 different places. So call it, you know, 3 30% tunings. Or, you know, you sort of shove things around, but at least I never get a feeling that there's something really great. Okay, but still, there are people who disagree, and you know, they could well be right. And if we turn on the LHC and we see all of the superpartners beneath 400 GeV, okay, that's an incredibly natural theory. We're all just freaking out for no reason. There was some good reason why all of these indirect experiments didn't show anything up. There's some beautiful structure in the supersymmetric theory. It's incredibly natural. And actually, I think if that happens, it would really give me pause. And would make me go back and start, even though logically it's not connected to the landscape, logically it's not connected to the cosmological constant problem and so on, but psychologically, if what we saw was an incredibly natural theory with a very smart mechanism built into it that none of us had ever thought of for making everything make perfect sense, I would say, okay, if there's a very smart mechanism even in little dinky particle physics, then maybe there's some incredibly smart mechanism for the cosmological constant too, and I'll shut up for a while. On the other hand, I guess I'm saying I have not found any of the, you know, streams of papers on HAP-PH on ways of solving the little hierarchy problem, at least so far, to me, particularly compelling. It's also possible that it is a natural theory. There is something that solves this big hierarchy problem, and it is a little percent tuned. It just is. Because while I've given you all these nice examples with hierarchy problems solved in a big way with no tuning, anyone who knows anything about the history of our subject knows that you can pull out examples from history to support any polemic point you want to make. And there are other examples, many other examples, of parameters in the standard model that are just a little accidentally tuned. No one knows why. Okay? Let me give you a bunch of examples. And and I'm not making any value judgment on whether or not these tunings are crucial for life or anything like that. Okay, I might make a comment about that in a second, but these are just facts. Fact: the deuteron. Okay, deuteron is a what is it? It's a proton and a neutron, right? It's a bound state of a proton and a neutron. Now it's made out of protons and neutrons. They're heavy, right? So everything in nuclear physics, the scales are at least hundreds of MeV. M pi is 130 MeV, right? The masses themselves are GeV. So if you had to guess, what would the binding energy of nuclei be? Typically, I would guess, 100 MeV. It's not 100 MeV. It's 2 MeV for the deuteron. It's a lot smaller. Actually, that's a little more dramatic than it seems. There's something much more striking in the scattering length. In the proton-neutron scattering length, the scattering length is much larger than you would expect from the Compton wavelength of the pion. Okay? Much, much larger, a factor of 50 larger than you would expect from the Compton wavelength of the pion. And actually, nuclear physics is littered with these examples. Because, this is a fact about nuclei, right? The first few nuclei, they're really sporadic. At least this is one of the problems I had when learning or not learning chemistry, is that, you can never keep track of, who the heck are all the nuclei? Because you have P, okay, I understand that. But we have PN, we don't have PP or NN, okay? Why is that? And it's sort of sporadic for a while, and then of course, as you get to many nuclei, okay, we have all of them, more or less. Okay? But the reason we have some of the light nuclei, not others, is because of an accident. It's because of an accident having to do with the range and strength of the nuclear force. Okay? The range of the nuclear, there's a strength of the nuclear force. Think of it roughly as some potential well. The depth of this well is set by the strength of the nuclear force. So G, let's call it G pi, coupling of nucleons to pions. Okay, that's set by that. This is set by the Compton wavelength of the pion. And why don't we have an NN or a PP bound state? We don't have these bound states because the range is so short that just the particle in a box kinetic energy is too much, and they overcome the barrier height and they escape. Okay? But that's because of a total accident. It's because of an accident between the strength of the coupling, the masses of the protons and the neutrons, and the pions. Okay? To illustrate that it's an accident, NN, I think, or is it PP? One of the two isn't bound. Do you know how much it's not bound by? It isn't bound by 100 keV. Okay? Isn't that amazing? All the scales in the problem are 100 MeV, and the amount that it's not bound by is 100 keV. Okay? And it's a total accident. If we change the parameters a little bit, if we change the pion mass by 1%, funk! We'd have dihydrogen, what the hell would it be called? I don't know. We'd have whatever that guy is. It would all of a sudden exist. Okay. There's all kinds of little accidents like that in the Standard Model in nuclear physics. The more famous example of that sort, which is related to, the more famous example of that sort is that we have interesting, complicated nuclei at all. Why can we have interesting, complicated nuclei at all? I mean, if you're very dumb, or if you're very naive, as certainly I am when I'm first learning about these things, you say, a neutron decays, right? So in empty space, a neutron decays. So why the hell do we have NP, or N's in anything? Well, reason why is because the nuclear binding energies just happen to be larger than, comparable to, the neutron-proton mass splitting. The neutron's a little heavier than the proton, but nuclear binding energies are comparable to that. That's an accident. That's a total accident. Okay? That's an accident that has to do with the relative proximity of the up and down quark masses to the QCD scale. I'm talking about the actual up and down quark masses Yukawa coupling times the weak scale. Okay? So if we made the quark masses, let's say, uniformly a little bigger, what would happen is the neutron would get a little heavier than the proton, so much so that the neutron-proton mass splitting would exceed nuclear binding energies. Okay? We'd have nothing other than hydrogen, or eventually helium. And actually, if you kept cranking up the overall mass scale of the light quarks, everything would be a delta plus plus universe. Okay, the delta plus plus becomes the lightest baryon, and that's the same as helium. Okay. Now, so how sensitive is this? Well, if we just jack up uniformly the mass of all the quarks by a factor of 3, that's it. Already, it's an all-hydrogen universe. Okay? So the fact that we have interesting, complicated nuclei is also an accident, a relatively sensitive accident. And if we change the weak scale, for example, if we change the weak scale by a factor of 3, let's say we've kept everything else fixed and we just jacked up the weak scale by a factor of 3, then nothing other than hydrogen. If we kept going, nothing other than helium. If we kept going, nothing other than the delta plus plus. Okay? The fact that we have interesting, complicated nuclei is then an accident that happens just because the value of the weak scale in the Yukawa couplings is such that the masses of the up and down quarks are kind of comparable to the QCD scale. That's a pretty sensitive accident. Regardless of what value judgment you want to make on it, I haven't said the word anthropic yet, okay? But there are just little coincidences in the values of the parameters of the standard model. And there's lots of them. There's a very nice book by John Barrow and Frank Tipler. It's called The Cosmological Anthropic Principle. And you can completely forget about the first and the last part of the book if you don't like the words anthropic principle. In fact, I, for a long time, despised the words anthropic principle, but I love this book because while the first and the last parts were the philosophical, I used to think crap, now I think maybe sometimes interesting, okay? Maybe not interesting, let's call it crap, okay? The middle third is wonderful. The middle third is just goes through all of physics, reducing everything to fundamental constants. Of course, they have a hidden agenda. Their hidden agenda is to show how everything depends sensitively on fundamental constants. So if you change things by a little bit, things change in some dramatic way. But still, it's just a very nice piece of physics, the middle third of this book. Just seeing how all the phenomena are reduced to just a few parameters that control long distance physics. And anyway, in that book, you'll see many, many accidents of this sort. Okay? So when you look closely at the parameters of the standard model, you see, I mean, at first blush, they look random and crappy. Okay? Many people try to find patterns in them. I've tried to find patterns in the pattern of fermion masses. Maybe it's like the Balmer spectrum, and some incredible pattern will emerge, and that'll be a key to some underlying substructure. Blah blah blah. That's been an old dream that no progress has been made on for 35 years. Partially because when you actually look at the masses and the mixings, they look a little crappy. They don't look like the work of a brilliant designer. They look a little garbagey, okay? At least to me. I can be more specific about what that means, but I do mean it. That there doesn't seem to be any magic or any real incredible relations buried in the 13 flavor parameters of the standard model, for example. On the other hand, interestingly, in some of those parameters, at least the ones related to the light quark masses, there are all these little accidents. There are little accidents that happened, which if they didn't happen, the world would look incredibly different. Okay. So that, to me, is more circumstantial evidence that we're not going to get the values of these parameters as solutions to some unique set of Diophantine equations handed down from above when we understand the ultimate final theory of everything. Because I would find it very strange indeed if all these parameters were fixed by the solutions of some equations. I would find it incredible that out of pure numbers, all of these parameters, m electron, m up, m down, the weak scale, lambda, all these things are in the end, the dream, right? The dream is that they're all pure numbers, right? Ratios of the Planck scale, there's some pure numbers. There's zeta of 3, pi, e, Okay, so there's a sequence of formulas like that. And then you plug in these pure numbers, and these pure numbers just happen to spit out a bunch of values which are, suitable for us to exist, for the universe to be complex and interesting, not empty. Maybe that happens, but if that happens, that would make me really believe in God. That whoever designed, someone designed these laws to spit out these numbers just so to allow me to. I'm very important. I'm hardwired into pi's and zeta of 3s. Okay. That doesn't seem plausible to me. Instead, it seems that it seems more reasonable that these constants aren't going to come out as unique solutions to some set of equations. But there's going to be lots and lots of solutions to some underlying set of equations, and then so these accidents can have a rational environmental explanation. But anyway, all of this by prelude to saying that it could be there are accidents in the standard model. There are percentage accidents in all sorts of parameters. Whether or not you like the words anthropic, it's just the fact that if you take some of the parameters in the standard model and mentally change them, and we know enough about physics to be able to predict what would happen to those universes as you mentally change these parameters, then the universe would change a lot. Okay? And finally, there are sometimes fine-tunings happen with no apparent explanation at all. The most famous example that I know of is the fact that the moon perfectly eclipses the sun. That's a complete accident. It's about a part in 10 to the 3, part in 10 to the 4, complete accident. And well, there's some dynamics, of course. It's not a total accident that everything lines up in the same plane. That's gravity and tidal forces and dynamics. The fact that the sizes ended up being what they were has no obvious environmental, anthropic, any other sort of benefit. If anything, it's the misanthropic or mis-virginotropic principle, because that near coincidence resulted in the sacrificing of a lot of people in different cultures over the years. Okay. Okay, but even sometimes accidents can happen. All right. So all of which is to say that maybe there is. So let me go through 3 possibilities. Maybe there is a natural theory of the weak scale, and it's damn natural. And it has some very cool mechanisms in it, and it has some structure in it that at least I haven't thought of, even though some HEP-PH paper might contain it already. And when the LHC finds it, they'll say, I told you so. Okay? And so it's incredibly natural. It has some clever thing that at least most of us haven't realized is there. That's one possibility. Another possibility is that there's still some natural solution to the hierarchy problem. It solves the big hierarchy problem from the Planck scale to the the Guth scale to the weak scale. Okay, so in a very grand sense, it solves the hierarchy problem. But at the end, it's got a little percentage accident in it, a little percentage cancellation between 2 things, and that's just life. Okay, that's also possible. Or maybe the problem with that, of course, is if that's happening, why should it stop at a percent? It's 10 to the -3, okay. 10 to the -4 is our eclipse. There's no really good reason why it should stop at a percent, but still, you say, whatever. Percentage things have happened before frequently. But maybe there's something more dramatic. And so that's what I want to talk about. Because in both of these examples, in both of the first 2 possibilities, we more or less know exactly what to expect at the LHC. This has been the story for 25 years, right? Low energy supersymmetry, or technicolor, or warped dimensions, which are the same thing, or large dimensions, which are basically the same thing. So strong dynamics or weak dynamics of some sort or another. But anyway, that's what we know, we've thought about it, we know the kind of signals to look for, we know what to expect experimentally. And even the scenario where things are tuned to about 1%, that's also something we know how to look for. That's also something we know to expect, because that's where our theories have been pushed for the past 10 years, okay? So almost all the theories that people study, and unfortunately, almost all the theories that our experimentalists put so much work into, seeing how you simulate this or that or other theory at the LHC, most of these theories are already tuned to the few percent level already. So we certainly know what few percent tuned theories are going to look like too, okay? But it's worth wondering whether there's something much more dramatic, whether, in fact, we're going to see an extremely unnatural theory at the LHC, and to try to get an idea of what such a theory might look like. Okay. So, the idea is then going to be that we're going to imagine the hierarchy problem is not solved by a dynamical mechanism, but is solved by fine-tuning. Okay? The weak scale is just finely tuned. Why should the weak scale be finely tuned? Well, here we're going to invoke an argument a la Weinberg for the cosmological constant. In fact, the standard model has two dimensional parameters, the cosmological constant and the Higgs mass parameter. Exactly those two dimensional parameters are the ones that cause us trouble. Weinberg has a beautiful story for one of them. Might there be an analogous story for the other? Okay. Might there actually be the same sort of explanation for both of them? And I just told you, so now Weinberg had a good story for why the vacuum energy had to be what it was. At least only changing the vacuum energy and nothing else, it can't be too much bigger than the observed value without the universe being empty. Okay, so that's a very dramatic thing that would happen. And so it's true, while the vast majority of the multiverse, the value of the cosmological constant would be bigger, it's empty too. So obviously we're not there. For the weak scale, I just gave you a possible explanation. This was an explanation that Donahue and friends talked about already 10 years ago, an anthropic or environmental explanation, which is that if the weak scale gets even a factor of 3 bigger, holding everything else fixed, atoms disappear. Okay? Because of the reasons that we just went through. So there is, interestingly, we have two problems, two big fine-tuning problems, and each one of those parameters is associated with some disaster. Okay, each one of them is pretty close to living dangerously, pretty close to living near an edge, where if they were too different and more natural, the universe would either be empty or devoid of interesting atoms other than hydrogen, or helium, or delta plus plus, depending on where it is. Okay? All right, so regardless of what you think of that explanation, operationally what that means is we're going to take the following rule for building theories. Okay? The rule is we're going to take effective field theories when they have relevant operators, dimensionful positive dimension operators. We will fine-tune coefficients of operators for which we can identify disasters if they weren't fine-tuned. Okay? So while I'm throwing out naturalness, I'm not throwing out everything. This does not mean that I can build, let me give you an example of theory I cannot build along these lines, okay, with this set of rules. I can't take a theory with 2 Higgses. I can't take a theory with 2 Higgses, both of which are much lighter than some cutoff scale. Because all I need is one of them to get a VAV. All I need is one of them to get a VAV and to, okay. If there's another one around, it's there for absolutely no reason. It doesn't affect infrared long distance physics in any way. So there's absolutely no reason for a second Higgs to be tuned. Okay? Now, so this is just a set of rules. I don't, again, my standards are low. I don't have to justify them in a deep way from a deep underlying theory. But all I'm saying is that there's a minimal way of letting fine-tuning in through the landscape, through the idea of a multiverse, by saying only parameters that you can identify a clear reason for them being tuned should be tuned, and other parameters should not be. Is that clear? Okay. So this is a new set of rules for model building. We used to play with gauge groups, particle content, branes, extra dimensions. Now there's another rule. The other rule is the landscape rule. Allow yourself to fine-tune parameters that you can come up with a long-distance environmental justification for. Okay. Now, so I have only 2 minutes, so let's dispense with the first model along these lines. So what is the first model along these lines? It's the standard model itself. Okay? So if we have the standard model itself, that's it, right? Apparently we don't need anything. If we take this point of view, we don't need anything beyond the standard model. Okay. Now, I'm coming to that. Okay, but there are additional things that we want in our universe, other than just electroweak symmetry breaking and particle physics. Okay, one thing that apparently we need to have is dark matter. So that's one thing that the standard model does not have. Now, of course, there's something else that going along the natural track, there's something else that in particular low energy supersymmetry gave us. It gave us unification of couplings. So this is why, when I say I sort of flip back and forth, when you stand from low energy supersymmetry from just a little bit of a distance, not even that much of it, just a little bit of a distance, there are, I'm trying to figure out how to say this nicely. I'm not sure I can say what I'm about to say nicely. There are very famous people who are very famous for very good reasons, who enjoy looking at supersymmetry from a distance, a little bit of a distance. And from a little bit of distance, it's glorious, okay? Totally beautiful, obviously correct, and, when you're as august as these people are, you can look at things from a distance and not, worry your little head about all these little nagging problems. Say, oh, nagging problems are for you, not for us with clear unification. And it's right. I mean, I'm very sympathetic with it because, come on, give me a break. What the F? It didn't have to happen. You have to have supersymmetry at low energies, roughly the TeV scale, to solve the hierarchy problem, and wham, the couplings just unify, right? That sort of thing doesn't land in your lap every other day. It's really a kind of percent level. It's a percent level prediction. A number of people are confused, by the way, because often it's said that there's a prediction for the strong coupling constant is only valid at the 10% level. But this is really completely wrong. Really, there is a correlation between the value of the strong coupling constant and the ratio of the two weak coupling constants, or sine squared theta. And unification predicts that things should lie along a specific line in this plane. And in this plane, you are just within 1% of that line. It's a stunning, amazing, beautiful thing. So that we get from supersymmetry, and supersymmetry gave us a wonderful candidate for dark matter. So supersymmetry has all these wonderful things going for it. What does it have going against it? Just all these nagging, crappy little problems from experiment. Okay. No flavor-changing mutual occurrence, no evidence, the Higgs hasn't been seen yet, et cetera, et cetera. Susie looks a little tuned. But, we have these, experiment is giving and taking away, right? It's, because it's also an experimental, we measure the coupling experimentally. The measured values unify. It's a fact about, an apparent astrophysical about the fact that there's, about the universe that there's dark matter. Okay, Susie gives us those two things, and then there are all these little nagging problems. So that's why, even though this argument was made 10 years ago by these guys, okay, Donahue et al. Said 10 years ago, there could just be an environmental solution to the hierarchy problem. We don't need anything. Screw you, Susie guys. I didn't believe it. And I didn't believe it, A, because, well, I didn't believe it because it just seemed too nice. These other two things that we got from supersymmetry seemed to be too nice. Unification and dark matter just did not have to happen. And it seemed reasonable that all the other little problems, they were just little nagging little details that would all get fixed up eventually. What happened in the intervening 10 years is that those little nagging problems got worse, experimentally a little worse. All the limits got better. We still didn't see the Higgs at LEP2. All the limits got worse. It went from being 10% tuned to percent tuned. On the one hand, all the little nagging things, and on the other hand, the cosmological constant was discovered. So that's a big shock from cosmology. And the landscape emerged as a very plausible place in string theory for fine-tuning and environmental explanations for fine-tuning to be relevant, especially given that the value of the cosmological constant was close to what Weinberg predicted. All of which is to say that what what the standard model lacks here is, what about unification and dark matter? So what I'll start talking about tomorrow, since I'm out of time, is classes of theories now. So pre the real emergence of the landscape a few years ago, these were just orthogonal possibilities. Either it's environmental, and it's just the standard model, or it's natural and it's SUSY. Okay. And what I'm going to talk about in the first part of the lecture tomorrow are new theories of particle physics inspired by the landscape, which are tuned. So they are on the environmental. So this is environmental versus natural. But they preserve unification and dark matter. And they have very specific experimental signals so that we can know whether they're either right or they're wrong at the LHC. So I'll start talking about that next time before proceeding to talking about cosmology.